Okay, so to rehearse, what we've talked about before is the fact that in structural modeling, very frequently we use that error term as a way of correcting for the effect of another variable. And more generally, if everything involved is circles, it's the same game with the same interpretation. And today what I wanted to do is to continue on through that handout and talk about quadratic linear effects and analysis of covariance and amplitude treatment interactions, because these are all examples of things that you have perhaps seen in your class in regression, and they also illustrate some more of the things that go into making a structural equation model that might be more appropriate. And following that, I rehearse one-way analysis of variance and other categorical models. And we're going to link up the logic between what you saw in those analysis of variance diagrams with ideas of suppression, redundancy, and orthogonality. So we talked a little bit about single factor models. Quadratic regression is also an example of a 3-variable model. And I tried to find a small data set that would illustrate this. And one of the ones that was out there was a study of fuel efficiency in miles per gallon. And if we're looking at this as a scatter plot, we can see that there's a functional form going on here, that generally speaking, if you drive your car too slowly, I drive my Prius really, really slowly, your miles per gallon is not going to be good. And there exists some optimal speed that you can drive at that will give you the best mileage. And as you hit the accelerator more, your miles per gallon go down. So in our model, notice that what I've done here is to center the data. And the reason that I did that was if you just take speed, the number 20, and square it and make a new variable called speed squared, that variable is going to be very highly correlated with the squared value. So in your mind's eye, you might think of a little Excel spreadsheet. As a matter of fact, let's do that because it's. So if, for example, I have speed and that goes 20, to give an example, and now I take this variable and I square it. I'm going to get a scatter plot between my predictors that looks pretty highly correlated. So notice in this model, speed is highly correlated with speed squared. If, for example, though, I start out at centering this, notice speed and speed squared, that scatter plot does not look nearly as linear as it did before. If everything were perfectly balanced, I didn't have, for example, this row, there's no correlation between speed and speed squared. So the act of centering is a trick that we do. Let's come back to the diagram in order to give ourselves predictors that are not correlated. So this is an example of I have a choice. I could, for example, take my raw data, in which case speed and speed squared are going to be highly correlated, and I know I'm going to be dealing with a case of redundancy or suppression. Or I can rescale the data to the mean. I can mean center speed and use that as a predictor. And that's, for one thing, it's good to take a look at what a polynomial regression looks like in a path diagram form. It looks very similar to our old friend, a 2-predictor regression. But this choice of centering is a theme that you'll find appears a lot in structural equation modeling and hierarchical linear modeling, we very frequently center our predictor variables so that they're going to give us a value that will reduce some collinearity among the predictors. The other reason to center comes from looking at the path diagram with the mean here, that in regular old regression that we talked about, the path from the column of ones to the dependent variable is the intercept. And that intercept has as its interpretation the value of the dependent variable when the predictor variable is 0. Centering gives us a number that is perhaps more useful to us, that when I center my predictor variables, the intercept now becomes the mean of the dependent variable. Said another way, remember we talked about in earlier lectures the fact that when I do a regression, the regression always has to go through the point mean of x, mean of y. And if I center the mean so that the predictor has a mean of 0, the intercept then has to go through mean of y. So in this data set, 33.76 is the mean miles per gallon that I observe across all of the observations in the data. The rest of the diagram is, as I said, just an example of a 2-predictor model. One thing that you need to remember when you're reporting results from polynomial regression is that the standardized values really only inform you about proportions of unique variance explained. There really isn't a scaling world that you can live in where the mean of one predictor has a variance of 1 and the mean of the quadratic term has a variance of 1. It doesn't work that way when you're dealing with functional things. You can, if you want, standardize, in addition to mean centering this predictor variable. You can standardize it so it's a variance of 1, but this variance is never going to be 1 as well.
So what's the reason for that? Why we can't do this?
Well, mathematically, that's a good answer to that. Mathematically, it's not going to work because you're talking about the first and the second moments of the distribution. And you can work out the math for some things. I mean, Goldfield and Quant, for example, published what the variance of a variable is going to be based on the variance of the linear model, the linear effect, if the predictor variable is normally distributed. But more generally, we just don't know what that variance is going to be. You can do some experiments in Excel. You can try to generate a variable that has a variance of 1 and then square all those numbers. And you'll find that there's no scale that's going to give you that. It's just a mathematical fact, kind of. That's all I can really kind of say.
So we can do the variance of quadratic portion as 1 and then let the others vary. Can this possible?
So to speak the language of chapter 3, we can mean center, that is, we can put the linear effect in deviation score form. And we can standardize the linear effect, but we cannot also then put the quadratic term into deviation score form and standardize it. So for example, the linear effect, that has positive and negative numbers, as we saw. If I square them, all of a sudden now, the quadratic effect has, cannot have a mean of 0 because it's the mean taken across a whole bunch of squared numbers. So that's.
So I have one more question. For this diagram on the screen, we centered the mean based on linear portion. Is that Predicts, okay. And the other thing is, so we can do this for quadratic portion instead of linear portion as well.
Mm-hmm.
Is that correct? Okay. I just want to be sure.
Right. So to kind of rehearse, this is the mean of the linear variable.
Mm-hmm.
This is the mean of the quadratic.
Okay.
And these things are the variance of the quadratic and the variance of the linear effect.
So I have another question. So the reason why the covariation between the two is 0 is can be something like that because they belong to the same line, like different line, but show different piece of information about a single line. Is this the reason why the covariation between the two is 0?
Yeah, I mean, looking at the values of this predictor variable, which go from 20 to 55, it's symmetric. So I can figure out a mean here. There's an equal number of negative and an equal number of positive values. So just as we were talking about in that spreadsheet, if we come back to that, notice that, if I can make that a little larger for everybody. Notice that in this diagram, all of the squared values are positive numbers, and the scatter plot here, the best regression line going through that is a straight line. Mm-hmm. So whenever we have an exactly perfectly symmetric variable, we can go to a covariance of 0. That isn't going to happen when we try to look at quadratic effects for any old variable. So if you were looking at IQ test scores or ACT scores, those are going to be skewed. And therefore, the correlation between the centered version and the quadratic version isn't going to be exactly 0, but it will greatly reduce the correlation. So the take-home message from this is, oh, I can do a regular old quadratic regression. And here's a path diagram. It's just a two-predictor regression like anything else. The seed for the future is the act of centering when you're looking at some variables will affect patterns of covariance and correlation between the predictor variables. And as a result, increases, just as we talked about before, it increases the power for detecting statistical significance of the regression weights. So to rehearse, if you've had regression with me or anywhere else, when you're doing a polynomial regression, we run our polynomial regression based on the centered values, and we make our conclusions about the statistical significance of the effects based on those centered values. You may, however, when you publish the work, report the uncentered solution, mainly because that's the regression weight that other people coming after you might use if they were doing some work with your particular predictor variable, because they're not going to be so lucky as to get exactly the distribution of X scores, of predictor scores, as you did in your particular study. And, this is a side issue, but you can always, use a little bit of math. Here's our regression weight. And if you take a derivative is a fancy word for saying I'm going to take this number, multiply it by the exponent, and reduce the power by 1. So 11 times x to the first, the derivative of that is going to be 11 x to the 1. That's going to be this number. 2 times negative 2 times x is going to be minus 0.318. I can then calculate exactly the value on x that's going to correspond to the maximum. It's going to correspond to this value that's going in centered version is going to be where this hits its highest point. That's not something essential for this class, but it again ties back to a discussion of polynomial regression when you had it. Next, let's take a look at mediational models. And I kind of spoiled the surprise here that when you're looking at mediational models, the estimates of the unique effect are nothing more than our old friend, the regression weight. So here's a model, which is a mediational model. That is, I'm thinking that the variable smokers look cool causes both last 30 days cigarette use and also causes the perception that smokers are more mature. And just as before, these numbers correspond to the mean of smokers look cool, and this becomes an intercept for smokers look mature. So let's just talk about this top part here. This retains its original meaning. It's the variance of this predictor variable. The mean of smokers look cool is going to be 1.7. And the reason nothing else is involved is if I go forward on this arrow, I cannot go backward here. If I go forward on this arrow, I cannot go backward here. So we're very confident that this 1.7 is only the mean of smokers look cool. Let's turn our attention to the mean of smokers look mature. Well, in that case, there's two ways to get from one to the other. I can take this path, 1.62, and I can take this path, 1.7 times 0.64. There's nothing downstairs again, because I can't, if I go forward on this arrow, all of these are backward pointing arrows. Let's try to figure out what this 0.51 means. Well, I'm sorry, let me take that back. Let's talk about this 0.64. What does this diagram say about the covariance of smokers look cool and smokers look mature? Well, that's going to be just like a single predictor model. 1.06 times 0.64 is the covariance. Having gone forward on this arrow, again, I can't go backward on any of these arrows. So rather than this being the covariance between the two, as we saw earlier in the chapter, this is now the covariance divided by the variance of 1.06. And next, think about what this diagram says about the variance of smokers look mature. Well, that's going to be this error term plus 0.64 times 1.06 times 0.064. So, in terms of what we're looking at, everything up here is a single predictor regression model. Now let's take a look at what this diagram says about smokers look cool, the covariance between that variable and the criterion. Well, that's going to be 1.06 times 0.22 plus 1.06 times 0.64 times 0.30. So again, because this is 1.06, and we talked about the fact that that is the covariance divided by the variance, and I've got the 1.06 here, multiplying this path by this path is the same thing as just saying the covariance. It's the variance times the covariance divided by the variance. So this number and this number are going to correspond to the same regression weights as we had before. The moral of the story here is regression models and structural models can be completely agnostic about the causal assumptions made in the predictors if what is of interest to you is the estimation of unique effects. Now, usually that takes a little bit of thinking, because in other classes and in other articles that you've read, there's a lot of talk about the arbitrary nature of effects and how you can produce different conclusions about direct and indirect effects subject to a particular causal structure. But we're breaking this down in simple parts. The first part is to realize that what's up here is a single predictor regression model. that this coefficient merely represents the covariance divided by the variance, and that therefore these numbers are going to be the same. Well, and we talk about that effect quite a bit. Well, what about, all right, so having cast a little bit of doubt about the value of necessarily drawing the distinction in a mediational model, what is it that we are doing that's unique when we talk about an indirect effect? Well, what is an indirect effect, first of all? This coefficient down here is a unique effect. It is how Smoker's look pool affects the criterion directly. A compound path coefficient that involves another variable is an indirect effect. This number times this number times this number. And we might be interested in the question of whether that particular path explains a significant amount of variance. Well, if you're playing with M plus, that's the way that you would specify the indirect model. So in terms of a printout, you'll get a total direct effect, and you'll get all of the indirect effects. And this is the estimate of the standardized effects that are associated with it. This is the estimate divided by its this is the standard error. And this becomes 409 divided by 0.044 gives me 9.29. And it is these coefficients that give me the statistical significance of the indirect effect. So in this case, in M plus, it also gives you the total effect and the indirect and the direct effects. This 217 is this, well, within rounding error, that 217. Okay. So usually at this point in the class, been doing this for 30 years, this takes a little bit of chewing, and people want to talk a little bit about what a direct and indirect effect is. So I will be quiet for a moment.
I think you can say this again.
Okay. So our direct effects are going to be all of the cases in this diagram where I go from the predictor variable to the criterion directly, that is, the variance times this, or the direct effect of Smoker's look mature in the last 30 days is this variance times that. And the indirect effects consist of all of the compound paths traveling from one variable to another. So in this case, Smoker's look cool, this variance times this times 030. And the product of those three numbers is what we're looking at down here in our indirect effect.
So I have a question here. Can you scroll up? And can you show the diagram? Yes, this diagram. So here, can we go from last 30 days, Smokers looks cool, mature, etc., by following this path? So A, 0.22 times, so without going through variance here. So can we just go from here, 0.22 times 0.64 times 0.62 again? Like,
so are you saying, sorry?
Can we do U shape without going to variance? So.
Okay, so are you wanting to do a covariance trip or a variance trip?
Variance trip.
A variance trip, so from last 30 days and come back to last 30 days?
Yes,
Okay, let's walk through that. So I can go backward on 0.22.
So the questions, can we go without taking this link here?
Yeah, So for example, like 030. So if I wanted to do the variance of 030, I can go backward and do 051 and go forward again. But when I go backward this way, 030 and 064, I can take this variance and then go forward and come back again. But I wouldn't take this variance component on that trip because I already had my variance component up here.
So my question is, can we do this without going through the variances? So can we just go directly, something like that? Let's start from, again, last 30 days and move,
Okay.
So move to a smoker's cool.
Okay.
So point 22.
Yeah.
And then without taking this link, can we
Right.
go through something like that? Can we take the road? Yes, this road, 0.64,
Yeah.
and then go back through BPAT.
No, I have to take one sling.
Oh, okay, I see. So this was my question.
Yeah.
So we have to take one sling all the time.
Yeah, and sometimes for these types of things, when you're trying to get it in your head, it seems to be easier for people to remember that you can go forward and you can go backward and then forward, but not forward and then back, by redrawing this diagram a little bit and making this an error term. Just make it a circle and point a forward arrow at it. And that highlights the fact that once you've taken a sling, you can't go back, which is another one of the tracing rules. But when you see that circle there and a forward pointing arrow, people kind of realize that in their head a little better. So that's kind of helpful. I mean, the diagram here is just written in the most parsimonious matrix algebra form you can do.
Okay, thank you.
All right. So let's talk a little bit about regression again. One of the things that's kind of funny, when I started out here many years ago, people would grill the doctoral student in their defense for saying, are you sure that your predictor variables are normally distributed? And the person would say, oh, well, yeah, I'm going to run a test to see if things are multivariate normal. And it's important to remember that that's not an assumption of regression. There is nothing about a regression or an analysis of variance model that assumes that the predictor variables are normally distributed. What is assumed to be normally distributed is the dependent variable's variance. So, for example, I might have a little study, a one-way group design. I might gather some data on people, 5 subjects, in each of 3 groups. And an analysis of variance model results when I draw the following diagram here. Well, that looks a little weird. Notice that this has 3 predictor variables in it, and there's no direct path from the column of 1s to the criterion variable. But look at what results here. You get 3 numbers out here, 3, 6, and 9. And those 3 numbers just happen to turn out to be the means of the dependent variable in your 3 groups. That is, when I draw the diagram this way, the resulting means of the dummy-coded variables are 1/3, 1/3, and 1/3, because what I'm doing is I'm putting in 3 new predictor variables. You get a 1 if you're in group 1 and a 0 otherwise. And I'm going to do that for each of the 3 groups. So that's why you see 1/3, 1/3, 1/3 here. Notice that inside of each of these variables, there's a covariance between these variables, and it is small and negative. And this is because if you are in group 1 and you receive a 1, that scatter plot of the dummy-coded vector for the first group is slightly and negatively correlated with the numbers from the other group. maybe it's helpful to come back and return to our old buddy Excel. And so if, for example, I have two predictor variables that look like this, well, what happens when I generate a scatter plot of those? Well, I got, if you are in group 0, you're in group 1. If you're in 1, you're in 0. That is, there's a negative slope that goes on between these. If I come back and I do it for the 3-group situation, dummy 1 and dummy 2, my two predictor variables, are going to look like this. And now I've got people, if you're in group 1, you get a 1. If not, you get a 0. If you're in group 2, you get a 1. If not, you get a 0. If you are in group 3, you have a 0 on both variables. So if I try to draw a regression line through this, I again have a negative slope between the predictors. So that's why what I'm seeing in this path diagram are small and negative covariances. So, in words, this is a path diagram that corresponds to good old analysis of variance. Other times, I might be wanting to treat one of my groups as a control group. Well, if that's the case, I'm going to do a slightly different diagram. If you're in group 1, I'm going to give you a 1 and a 0 otherwise. If you're in group, I'm sorry, this is the second one. If you're in group 2, I'm going to give you a 1 and a 0 otherwise. If you're in group 3, I'll give you a 1 and a 0 otherwise. But I'm going to leave out that dummy-coded vector that gave you a 1 and a 0 otherwise. So now I only have 2 predictors in the model, but I have drawn a mean and intercept from this group down here. Well, notice that I got the same number for the control group as I had above. These regression weights now change a bit because they are now telling me how many points above or below the control group group 2 was relative to group 1, and group 3 was relative to group 1. So to rehearse, I'm kind of coming back up here in the data, this is the mean of the first group. If I treat that as a control group, and only look at the 2 dummy-coded vectors from groups 2 and 3 and point an arrow from the column of 1s to the criterion, that intercept will have as its interpretation the mean of the control group, and the regression weights that come out of the other 2 dummy-coded variables will tell me how many points above or below the control group that particular group is. Notice I still have the same covariance between the dummy-coded vectors as I had before, but it's just another model you can draw. So that's the Anova model, and that's dummy coding relative to a regression model. And the reason we call it a regression model is you're estimating an intercept. All right. Now, finally, we can also talk about orthogonal coding. Orthogonal coding consists of numbering schemes where one predictor has a 0 covariance with another predictor. So in this model, an example of an orthogonal code could be, hey, what is the mean of the first group different than the mean of groups 1, 2, and 3 taken together? That's one question I'm asked. And the second question I can ask that's orthogonal to that is is the mean of group 2 different than the mean of group 3? Well, in order to do that, I'm going to now make some effect-coded variables, that is, variables that have 1s and -1s. And the first orthogonal contrast I can draw will be, is the mean of group, I will give you a 2 if you are in group 1, and a -1 if you're in groups 2 and 3, so that the mean of that effect-coded variable is 0. And the second orthogonal predictor I will make is, if you're in group 1, you get a 0, and if you're in group 2, you get a 1, and if you're in group 3, you get a -1. And notice when I do that, I have a 0 covariance, because the cross product of that system is going to be a flat line. It's going to be, a scatter plot will look like a flat line. The interpretation then of orthogonal coding for the intercept is going to be the mean taken across all 3 groups. This coefficient will tell me how many points group 1 is relative to groups 2 and 3. And this coefficient will tell me how many points different group 2 is from group 3. And that's, an example of an orthogonal contrast. So effect coding is yet another strategy, and we're going to use 1s, 0s, and -1s. So in effect coding, if you're in group 1, I'm going to give you a 1 for this first predictor. If you're in group 2, I'm going to give you a 0. And if you're in group 3, I'm going to give you a -1. And turning to the second predictor, if you're in group 1, I'm going to give you a 0. And if you're in group 2, I'm going to give you a 1. And if you're in group 3, I'm going to give you a -1.
I have a question. So this one, for our coding strategy, it reminds me the quadratic one. First you go, you are up at 1, and then you move to 0,
Yeah.
and then -1. So is there anything like something, I don't know, like quadratic, or I don't know how to explain, but it reminds me something from our previous classes.
So, okay, yeah, that's fine. So if you were more aggressive, you might say, what is this good for? Why do I care? So let's take the question as that. Dummy coding was using a system of 1s and 0s.
Mm-hmm.
And if I have all 3 variables coded with 1s and 0s, I have to use the analysis of variance model. That is, I cannot estimate an intercept on Y. But the advantage is it gives me numbers that I care about, that is the means of the 3 groups. If I come downstairs and use my system of 0s and 1s, but only use 2 of them, the intercept mean becomes the mean of the control group. That is, I leave out the vector that had the 1s in it. This regression intercept is going to have as its interpretation, oh, this is the mean of the control group. And the mean for the second group is going to be 1/3, well, is going to be 3 plus 3, or 6. And the mean for the third group is going to be 3 plus 6, or 9. Mm-hmm. And those are kind of handy things. In other words, if I really am only interested in the treatment effect, I might dummy code. Mm-hmm. And if I'm interested in looking at orthogonal codes, I might think of questions where the covariance between, I'm going to use 1s, 0s, and -1s, or -2s and 1s, no, just any strategies such that the mean of that is going to be 0, to ask questions that where the covariance is 0. And in this particular 3-group example, example of an orthogonal code is 1 different than the mean of 2 and 3, and is 2 different than 3. Now in effect coding, I'm going to use 1s, 0s, and -1s. One of the groups, in this case group 3, is always going to get -1. And I will use 1s and 0s to identify group 1 and 2. And the reason I care about that is that's going to give me my answers relative to the grand mean, the mean across all people in the study. And the answer I get out for this group will be how many points above or below the grand mean, that is the mean taken across all the people I looked at. So in this little example, the grand mean was 6, and group 1 had a value of 3, that is 3 points below. And secondly, this group was coded as 0 if you're in group 1, and 1 if you're in group 2, and -1 for group 3. Well, this 0 means that group 2 scored exactly 0 points above or below the grand mean, the mean taken across all 3 groups of 6. And so these predictors that we have to express categorical data are chosen, the coding strategy is chosen to provide coefficients that answer the question that we want to have.
Okay, I think I understand it.
Okay.
Thank you.
And so that this little section is, and here's what analysis of variance looks like. Well, we have a bit of time. We can start with our next example, which is analysis of covariance. The nice thing about analysis of covariance in this class is that we can look at it and say, well, that's just the same old structural model as we had before. It's another 2-predictor regression. It's the marriage of a continuous predictor and a categorical predictor. Now, I tried to go out and look for an example, and there is a book that I got called Small Data Sets. And this was taken, I think, from Scotland, and they were slaughtering sheep. And you have rams, the males, and ewes, the females. And we're looking at weight, and we're looking at the percentage fat that resulted from the slaughter. And as we're looking at this, we can see that there seems to be a nice linear relationship. The heavier the sheep, the more the fat. But as we look at this example, it seems that all of the ewes have, store more body fat than the rams, because the rams are busy doing ram things like butting each other in the head. Well, here's my data. Here's my weight. Here's the fat that results for the ewes and the rams. Well, what I want you to draw your attention to is, here's the path diagram. Well, that is just a regular old 2-predictor regression. It's just that I have a dummy variable here that codes for sex of ram, and a continuous variable here that codes for the weight. So, and as you can tell, I'm kind of a curmudgeon when it comes to statistical analysis. Whenever you are doing an analysis of covariance, it's important for you to assumption check all of the assumptions of a continuous regression predictor. So coming back up here to our scatter plot, this is a nice scatter plot. But when you're looking at data and you want to do an analysis of covariance, you need to assure yourself that this relationship is mostly linear. If it's curvilinear, analysis of covariance isn't appropriate. And you should also assure yourself that the scatter plot of the continuous predictor for one group looks pretty much the same shape as the scatter plot for the other one. Now, this is a small data set. But if, for example, you were dealing with a few hundred people, and not to dwell on alcohol too much, you're looking at scores on a personality, say a reasons for drinking measure, and how much people actually drink, you might find that that regression slope looks a lot different for the men than the women. And sometimes that regression gets offset because the men are scoring differently, elevated more on reasons for drinking, say, than the women. And some inspection of the reasonableness of regression needs to happen. But the end of the story here is, if you're doing an analysis of covariance, this is your path diagram. And these coefficients then represent the unstandardized regression weight. And this represents the amount higher or lower of U's relative to RAMs. And this represents your standard intercept. So this would be the predicted fat of a sheep, which was a ram, which had 0 weight. Well, maybe that coefficient isn't something you're particularly interested in. I didn't talk about it here, but you could, for example, center weight such that it would then have a mean of 0, at which point this intercept is going to have as its interpretation the fat value of the average U. There's the path diagram. If you're using this in GLM, these are the numbers that you get out. And I only do that because it draws attention to the fact that these numbers are exactly the numbers that you had upstairs in the path diagram if you'd analyze it using, say, Onyx or M+. Let's stop here because we're at time. We'll take this up. My objectives for the next time are to finish this part, to talk with you about aptitude treatment interactions. That is, what happens when the slope of the regression line is different from one group than another. And we'll wrap up with a summary of the major points that have gone on in this particular chapter. At that point, we'll get into assumption checking. And my reason for doing this is assumption checking is an important thing to do, just as it is for everything in structural modeling, just as it was for all of your regression and Anova classes. The reason I spend time looking at this is that very frequently people come into this class and they say, well, we only had one lecture on it and we never assumption checked. So I hope to provide you with the discussion of why you want to do it. And I hope to provide maybe some doubts as to whether everybody you know in your professional life actually knows how to do a regression or an Anova anyway, okay? All right, I'll hang around here and deal with any questions people have. If you're having trouble running Onyx and so forth, let me know. Other than that, I'll see you on Wednesday.